the sound, please. Yes. I think there's delay. Hello, everybody, and welcome to a new Final Projects presentation by our Masterclass students. Today we have a very exciting ceremony because we have 4 different projects using different robots and different labs. So yeah, I'm sure that it's going to be very exciting. And yeah, as always, I encourage all the audience to make your questions to our students, because at the end, after their presentations, we are going to leave some time for a Q&A session. And yeah, I'm going to be picking questions from the YouTube chat. I'm also going to make my own questions for the students. So yeah, please give us your feedback and leave us the comments there in the YouTube chat. So yeah, let's not lose any more time, and let me introduce the first final project of this ceremony, which is going to be delivered by Vallab, and the name of the project is CometBucks. Every nerd deserves his coffee. I like this sentence a lot. So yeah, let's say hello to Vallab so that himself can start talking about his project. Hello, Vallab.
Hello, hello everyone. Can we start with the presentation?
Yeah, go ahead. It's all yours. Audience is yours.
Yeah. I hope my screen is visible now.
Yes.
Yeah. So let me start with this. Did you know that more than 70% of nerds are introverts? Actually, these introverts mostly, as many of you know, that more and more of the scientists and people who invent things are mostly introverts, and these introverts face a lot of trouble going into public places, talking to other people. And as everybody knows, most of the ideas and companies, startups are born in coffee shops, and that is not a place for introverts, like where you have to face another people. A person who has very good speaking skills comes and talks to you, where this person is not very good at. So I introduce to you CometBots, where you don't have to face anyone. You just go and get a coffee from a robot. Let's straight away go to the robot. Let's see how it delivers our coffee and how our coffee shop works. I hope you're able to see the robot.
Yes, we can see the cameras there and the terminal also.
Yes, cool. Let me launch my project. Cool. Everything is launched. Let's go and launch our website. And we are running a promotion for Robotics Developers Day. Whoever registers for Robotics Developers Day get their free coffee.
Nice. I really love that.
Yes. So I have registered. So I'm claiming my free coffee. And it's so intuitive. You don't have to do anything. Just go and click the button. So you can see that it has detected the barista, and it's going to pick up and drop the coffee. And we also have another option. We can cancel our order. Nerds are always famous for changing their minds whenever they want. They can cancel their order. So the robot picks up the coffee and puts it back, so it can be delivered to someone else or thrown away. Cool. Now that we have completed the demo, we can go through how I completed this project.
Yes, I'm eager to know more about it.
The first challenge that I was facing was this particular UR3 node has multiple launch files. It has move group, it has RViz, it has CV node that has to take capture the barista bot and find the coordinates, and it has to uh, control this, move it to by sending commands, Cartesian commands, and the trajectory and everything. So it has multiple nodes, and at least six to and also the web video server and ROS bridge server. It has at least like 7 launch files. So handling all of them in a single terminal, like we used to do, is also a trouble. Like if I handle the move group and CV in the same terminal, the robot gets confused and it couldn't operate. So I had to throw everything under separate terminals and operate. But opening like 7 terminals would not be ideal for a scenario like this. So I used the ROS option to open shells, the different shells. So you could have seen in the desktop terminal that it has opened like 7 different terminals, and it has operated from there. So the next part is the 3D perception using the Intel RealSense camera D415, which is capable to find the depth using the stereo vision it has. So this formula that Intel itself has provided is very useful to calculate the coordinates of the particular pixel that the Intel camera is looking. There is an RGB camera within this Intel D415. which can be used using image pipeline that I followed, like I converted into grayscale, having some Gaussian blur and some other features like that to eliminate thresholdings and everything, to eliminate all the unnecessary items and just apply the Huff transforms to identify the important circles, the slots that I'm interested in. So after finding the center of the slots, I use this formula, which the center as in the U and V are the pixel coordinates, and the CX and FX and CY and FY are the intrinsic camera parameters available from the camera info topic. The Z information is available from the depth image that is captured. So the 16-bit image, 16-bit unsigned integer for every pixel is representing the distance of the pixel from the camera. So using this, we calculate the X and Y. This X and Y can be multiplied with the TF matrix, TF position matrix that we get from the base of the robot to the camera. Using that, we can find this XYZ, the global XYZ. But this directly gives the position of the interested pixel in the real world, in relation in the ROS world, in relation to the parent frame that we are interested in. And after that, it's quite straightforward. After finding our target, it's quite straightforward, because we know where the cup is, where we have to take the coffee, and we know where to deliver it now. It's all simple math from here. I use the move joint feature of the move it API to pick up the cup, to go to the cup, and Cartesian coordinates to move closer to the cup and pick it up and retract. Then I use the move group API to move it closer to the BaristaBot. Now the problem arises. A very common problem that I was facing earlier was the robot when I try to control it using Cartesian coordinates to drop it inside the BaristaBot slot. It started making some weird movements. It started spinning the whole way around. And after discussing with other students and some of the with the instructors, I finally got a useful suggestion from Mr. Girish, that solving these coordinates one by one solves a great hassle in this. Like I solved it X first, Y first, and the Z last. It had a unique advantage. Even if it couldn't reach the Z completely, the move it to API did not throw an error. Even if you, for example, if you want to travel to 2 meters, and the Z reach is not it is not possible to reach 2 meters, but it doesn't throw an error, or it just goes to 1.8 meters. The rest of the 0.2 meters, it just stays there. So this was a, even though it seems like a bug, it helped me a lot in solving this project. So so that it doesn't make some weird actions and spill the coffee all over the floor. And I use this to drop it there. And the reverse of this also, like picking up the coffee from the BaristaBot and placing it back is just the same. I solved the Cartesian coordinates one by one. X first, Y second, and Z last. And this is the web framework that I used. The web page is in contact with all my nodes using the Raspberry server. all these nodes that are running. I've not represented all my nodes, but to give an idea, the UR3 node is my node that that operates this movie to API, and the fine cup slots is the CV node, and the web video server was capturing the image. And I was not interested in showing the same image from the D415, so I generated my own ROS image, and I was showing that, broadcasting that. It had a refresh rate problem, so the image in the video server was kind of stuck for most of the times. I think that was the improvement that would be needed if I have to improve this project in any way. So this is the representation of the web video server. It just operates in this fashion, like it can capture an image and transmit to the web for ROS robots. And this is it. I would like to extend thanks to so many people, but telling their names would at least take 10 minutes, but I'll just give a short note. I would like to thank the organizers and instructors, Alberto, my instructor, and Ricardo in the lab. He was supporting me for a long time. He helped me debug whenever there is a problem with the robot. He would help me. And Girish, thank you so much. You supported me, and with a lot of patience, yeah, you cleared my doubts. I hope you keep doing this for many other people. And my fellow students, some of them who have been a good inspiration for me. And finally, my friends and family, thank you everyone for supporting me during this process, as it was not so easy coming here. Thank you so much. Yes, I'm open to questions, Alberto. I am done with the presentation.
Okay. Hello. Okay, so you can share your camera again if you want, Vallab. So that we
Yeah.
proceed with the Q&A session. That mountain looks very nice, by the way. That.
Second, let me stop. Yeah.
All right.
Yeah.
So yeah, first of all, congratulations for the presentation, Vallab. Then now is the moment for the audience. In case that you have any questions, you can leave them in the chat so that Vallab can answer the questions. Let me start myself with a couple that I have written here. So you were explaining here now at the end of the presentation that you were solving the Cartesian coordinates one by one, right? First X, then Y, then Z. Yes. So when you were doing the demo, it looked like the robot, first it went to one coordinate, then it moved like in the A axis, and then it went down. So this is what you are referring to?
No, finally, actually, when I went to pick up the cup, it was moved joint. It was just joint positions. I was picking up the cup using moving the robot down using the Z coordinate only. I was not moving everything else.
And then it's for releasing the cup that you do that.
Yes, Cartesian coordinates, solving it one by one. That was a huge trouble. Like it was spinning all the time. It was making weird movements.
Okay. And another one is that, so does your program support releasing the cup in different holes, or it only supports one? Or
no, here's a catch. It is like a catch 22. It supports releasing it in all the holes, but there is a problem. Due to the reach of the robot, I cannot pick the cup back from all the slots. I can only pick it up from 2 slots in this robot in this position.
I see.
So I had it locked. I didn't give the feature out but I was planning to have an option to select the place where you can drop, but having that means I cannot use the pick it up back.
Okay, yeah, it makes sense. So let me try to have a look here at the chat questions to see. Yeah, this is another one also that I had there annotated. So in when you were showing the image, there was like a video streaming of the hole detections there. So is that being streamed live or?
Yes. It was being streamed live. Yes.
Okay, and you are generating that with OpenCV or?
Yes, it was generated using OpenCV.
Okay.
That was the challenge that I was facing. Like I even tried increasing the refresh rate. I tried posting this message. I checked the frequency of the D415 image. It was sending like 5 times per second. I started posting the same images 5 times in a second, and still the images were not getting updated in the website. If I post the same stream, the D415 stream, it is working. But I had trouble posting my video. Yeah,
Okay.
that was the trouble that I was facing.
Okay, so let's see. Yeah, so this is from one of our students, which from Ahmad Kurdi. I know that name. And he's asking, how did you constrain the gripper orientation so that it doesn't tilt the cup as the arm moves?
When you're using Cartesian coordinates, uh, the gripper coordinates are actually limited. You cannot the trajectory is planned according to the Cartesian coordinates. So just by using Cartesian coordinates, we can limit it by from moving to any other position. Rather than it only moves to the position that we say.
Yeah, so basically you pass a series of waypoints to go through, right?
Yes.
And
We calculate the trajectory based on the positions that the gripper has to take.
yeah,
And
let me have here.
I wanted to show this picture. Sorry. Yeah, because the stream catches this image as lost. It had to show this image as soon as I clicked the cancel bot, but if you see the image in Arvis, it would show this image, but now it's not being shown.
So when
Yeah.
somebody cancels the coffee, there appears also this image of this sad robot, right?
Yes. My baristas are very sensitive, so they get
Yeah.
sad.
Yeah. Okay. So I have another question. So based on your experience working on this project, so what things would you change or improve in the real setup? I'm talking now, in order to make the whole system better. So how do you think it can be improved?
I was facing a very primary problem using this robot. I think Rodrigo would agree with me. It has a very sensitive sensor in the gripper. It just stops like it. Now I have to wait for someone to come and reset the robot. They have to restart it. I really had this thought in mind, like I should have changed my project to making a ROS controlled switch for the robot, so that I can just switch it off and switch it on using a ROS command. That in the real setup, I would really want that to be implemented, so that because when you book the lab for the weekend, and the first thing that you do Saturday morning 10 o'clock is the robot just takes the cup and pushes it against the table. Now it's stuck. Nobody's there in the lab for the next 2 days, and you can't work in the weekend.
Yeah. So that's a very interesting point. But actually, maybe you don't know this, but actually the Gripper is not working with ROS to control directly, which is a limitation. Okay, so
yeah, I agree with this point, Alberto. My point is like we can have a remote power switch for the whole robot setup. So you can just turn on, switch it off, and switch it on again, so that it reboots and all the errors are gone.
Yeah. You mean that you have this switch from your side, right?
Yes.
So that yeah.
So we can just hook it up with a small servo motor or a Wi-Fi controlled MCB that we can just program it and make it a ROS2 service. So you can just ROS2 service call send goal to this topic, this particular service, and just you can just switch it off and switch it on again.
Okay, so let me pick here. Okay, let me pick this one about Girish. Let's say he says, "Could you show us again the image processing pipeline?"
I don't have a slide of the image processing pipeline, but I can show it in the code.
I think I mean he means this in your web page, what you were showing in your web page.
In my web page, I was not showing the pipeline. It's just the end result. It's just the color image from the D415 with Circle Smart. It just leaves out the one circle for it's going to drop. Okay, I can launch it again. 1 second.
Yeah, let's see if Girish specifies exactly what he means.
1 second. I think the barista robot anywhere on the screen?
Now, no. Now we see you. Now we are seeing you.
Seeing me? Like, I don't understand. What's that?
Yeah. So now you are not sharing the screen right now. I think.
Yeah. I'm not sharing the screen. Okay. Let me. I've just closed the robot. I'll.
Okay.
I'll ask the. I need to connect the robot. 1 second. In the meanwhile, I can answer any other question.
He says, no, I was waiting for the clarification. He says, I just want to see the image processing happening live.
Image processing happening live? Okay. I don't understand what he means happening live, like each and every step of the image processing.
I don't think so. I guess. Yeah, I still think it's the final result.
Oh, final result? Okay.
Yeah. Rodrigo says that he loves the images. By the way, he's AI for the win. So did you generate that images with AI?
Yes. Using ChatGPT.
Yeah.
Okay. Let me just post the final image. Press a zoom. Yes, here. Please connect. Yeah.
Okay. So here it's detecting the whole let's say surface, right, of the robot, which is marked in yellow. And then each hole it's being marked in pink.
Yes.
Right, and then you are marking inside each hole with this light blue or.
Yeah, the center.
Mm-hmm. Okay, and are you? So can you explain a bit more on these detections here?
Yeah, how I approach this issue is like I've taken a single frame of the D415 color image, and I started by converting to grayscale, then applying a threshold. So I avoid all the other unwanted informations outside. And then I apply blur, Gaussian blur, and median blur. And the result image, I apply the Huff transforms algorithm to find the Huff circle, to apply and get the circles. Like I just give them, there is an option to change the minimum and maximum diameter in pixels. So I apply the Huff transforms twice. So it finds the base circle. One time it finds the base circle, and one time it finds the individual cup slots.
Okay, okay. And can you also show us, Vallab, for a moment, what you were talking about at the beginning of the presentation, after the demo, about all these things with the several launch files and how you integrated everything?
The launch files?
Yeah, that you had to launch several things in different terminals and so on.
Yeah. I'll show you the. One second. So if you see here, everything is running in its own terminal. This is the move group, and this one is the images captured. And so it's pretty much there are like eight terminals, eight individual terminals.
Jesus.
And there is one terminal for launching the website. So it goes to the particular folder and just launches this command python 3-m http server. And there's one for the CV processing, and finally one for Arvis.
Mm-hmm. Okay.
So these are the setup. Like I can show you the code as well if you are interested. Like
No,
for
no,
the
no,
launcher.
not needed, Balap. So there is one last thing here that the
Mhm.
Girish, also Ricardo, are saying that we can maybe try and see if it if your program is robust enough to support it. So it's to move a little bit the barista robot
Uh-huh.
and see if the perception is robust enough.
Okay.
So I don't know if somebody is hearing me and can do that here in the
Let's try.
office.
I have not tried, but let's see.
Can you put the cameras to see if? Okay, yeah, there we should see somebody.
Okay.
We should see somebody arrive there and move.
Okay.
I don't know if maybe Ricardo or Rodrigo, if they are hearing me, can do that.
Yeah.
There we have Rodrigo. There.
Yeah.
Okay, there
Let's
we
see
go.
if it can
Yeah,
reach there.
let's
Yeah, and
see.
also ask them to put the cup back, so I don't have to pick it up from there.
No, you don't need to pick it up again. So
Yeah. Okay.
just let's see if the perception supports it.
Okay.
This is a good final testing for the project.
Yeah. It's not good idea to test it now. Yeah. Let's see. Is there a cup in the slot? One second.
Uh,
Okay. Yeah. Even I'm eager to see what will happen. So the solving it by one happens after this.
yeah, I see.
Yeah, it works.
Mm-hmm. Okay.
Now I don't think it can reach to pick it up. but I can try. I can see if it can reach to pick it up. Let me just
Let's
see.
try. Let's see. Yeah.
Yeah.
Yeah. Probably. Yeah. Yeah. It might be a bit too far away, but
Yeah.
we'll
That's too
see.
far. But it won't give an error. That's the issue here. If we are solving it one by one, it's not going to throw an error. It won't reach that. That can happen. Yeah, it didn't reach. It didn't
Yeah.
reach.
Okay. Yeah.
Yeah.
Yeah. Okay. All
Yeah.
right. So I think, yeah, I think we can leave it here, Vallab. Very cool and interesting project. Thanks again, and congratulations for reaching this point of the final project, which is the end
Thank
of
you.
the masterclass. It's been a long journey, but yeah, you are now at the end, and yeah, next steps will be the internship. So we will be talking soon about that, and yeah, let's do a final applause there.
Thank you, guys.
All right, Vallab. So good job.
Yep.
Bye bye. All right, so we are done with the first presentation by Vallab. Very cool presentation, and we are going to continue now with the same setup. We are going to stay at the Starbucks cafeteria, but we are going to see another student's project. In this case, it's going to be the project by Abhishek Verma, and his project is titled CafeteriaBot Project, Solution and Insights. So let's say hello already to Abhishek. There we have him. Hello there, Abhishek.
Hello, Alberto. How are you?
Hello. I'm eager to see your solution to the cafeteria project. So yeah, let's go ahead. It's all yours. Let's not lose any more time.
Yeah, definitely. I think it's a very good day to be, right? And I'm very eager to present my solution to our audience, right? And the project which I have picked is CafeteriaBot, right? The reason for picking it up is very simple as well as intriguing, because it comes with its own set of challenges, right? And with great challenges, you got great learning opportunities, and that is one of the reasons why I picked this project, right? And let's not waste any more time and start directly jump into the project, right? So if you see the project which we are talking about, right, it is a cafeteria bot cleaner project, right? And the idea is that what we are going to do is that there is a table which we have to detect, and we have to dock that table, pick that table, and finally take it from its location, wherever it is, has been found, to the next room, which is just adjacent to this room, right? And it will signify that we have, you can say, like we have automated the complete task of picking up to the drop, right? If we talk about in a very high level, right? But as I said, this project itself has given a lot of, you can say, a learning opportunity to me, right? And uh, the why I'm saying is that because if you see, we usually have, when we talk about lidar data, right? Uh, we have a data which is gives you the obstacle distance along with the intensity of that particular obstacle, which it has reflected back. So, but in this case, we do not have that, right? There's a lack of a laser intensity data, right? So this is one of the very major challenge, although it has given me a very good, you can say, an opportunity to go dive into the laser data, right, itself, and also have opened a lot of new avenues and new, you can say, experimentation, which I have done to make this project work, right? Uh, Second thing which the challenge which was there is the detection of that particular table, right? As I said, if you do not have an intensity data, right, it becomes a little bit difficult. right? So to identify it from the rest of the group, right? And to that, why I'm saying that, because if you see the table itself has 4 legs, right? And similarly, a chair can also have, a sofa can also have, a couch can, and or even the other tables can be of a similar structure. Makes it very extremely difficult to figure out whether we are docking the right table or not, right? Similarly, if we talk about, we have to be very precise in control, right? As this is not a stationary robot, right? We have to move this particular robot from location A to location B, right? So it needs to be very precise in control, right? Which comes with its own set of challenges, as we will discuss about once we move forward, right? So this is whole about problem statement, right? If we talk about, right? Now the question arises that how are we going to solve this particular problem, right? And to that, solve this problem, right, to achieve the target robot behavior, right, what I have done is that I have divided this particular project into multiple segments, right? One of them being the navigation part, right? Second one is the detection part, which is the detection of the table, right? And finally, the control part. So when I talk about navigation, it usually on a high level, it means that I'm using a nav2 set, right, to to make the robot, you can say, localize, right? To do the path planning, to you can say to move from location A to location B with the help of map data, right? So these kind of things are handled by navigation system, while the detection is majorly responsible for figuring out what we have. So for example, to figure out the weather table, we are able to find the table on the map itself, right? Where the table is, how does that table look? Things like that is something which detection system take care of in general. Similarly, if we talk about robot control, right? Control is a high-level control node, right? This is something which I have to build from scratch, right? I have to design my own framework to perform a couple of activities. And the activities which I'm talking about is the patrol behavior, dock behavior, undock, move, right? So things like that is something which is managed by the control system, and it is using state machine, which we will deep dive into the couple of next slides, right? So this is how I'm approaching the problem from navigation, detection to control, right? In three particular steps, right? So navigation itself is you can say is not a very, you can say, star of this particular show, right? We are talking about when we talk about this particular project, right? Navigation itself is although it has its own challenges, right? But detection definitely have much more than that, right? For detection, what I use is that I have divided again the detection system into multiple subsystems, right? And when I talk about subsystem, it's more or less a node which we are talking about here, right? And detection system works into the 3 segment approach, right? Where first one takes part of the filtering, second one takes part of clustering, and third one is responsible for polygon detection, right? So filtering is when we are trying to reduce the data, right? We are trying to reduce the noise also in the data, and we are trying to see if that particular data can actually a table be represented by that data or not. And when we talk about clustering, what we are trying to do is that we are trying to group that particular laser scan data or laser scan points into cluster and potential objects, right? Moving forward, we have detection, which is finally using those clusters to formulate a particular, you can say, hypothesis whether a particular object is actually a table or not, right? So this is something which again has a lot of, you can say, R&D has gone behind this to find the appropriate to drive a particular mathematical formula to represent that particular table, right? So moving forward, we have filtering, which is the first step of detection system. And what exactly we are doing is that this is a plan. Like what we have done is that since we already only have distance data, we do not have intensity value with us, right? So what we are doing is that we are using occupancy grid data, which we already have. So once you set up nav2 navigation, right, we have a map data with us. We know where the robot is going to be. And I'm using that particular data along with laser scan data and then superimposing one on the top of other, right? And then using it to segregate data like scan data into a very much cleaner data, which is scan filter, right? So if you see on this particular site, let me just, yeah, this particular slide, right? Black represent that the space is occupied, white means that the space is free, right? And if you see this is similar, which is the map data, right, which is without mask. And if you see red one is coming, right, which represents that the data is not valid, which means that it is either on object, which is not in a free space. And the green one, which you see is something which is coming as a free space, right? So how effective is this particular approach, right? Turned out that it is very extremely effective, right? And if you can see this particular data, right? If you see the green one is the raw data, which is kind of coming from laser scan topic, right? And the filtered, which is coming in red, right? And the red one, if you can see, it has reduced drastically, right? Compared to what robot is seeing in journal, the scan filtered data is pretty much, you can say, clean. And we can utilize this data to for the next step, which is the clustering part, right? And so filtering it out actually helps to reduce a lot of computation in general, right? Because it's a, as we know, right, robotic system in general runs in cycle, right, in a particular frequency. And to make it computationally effective is very much important to like keep an eye on, right? So moving forward, what we did is that once we have seen that we have that data, right, which is a clean data with us, which is represented in green, I'm performing a clustering on top of it, right? So clustering we are doing, the story behind this is that I have tested around 6 clustering algorithms, right? And finally, I'm using a distance-based clustering, which is computationally very effective and as well as gives you a very high accuracy, right? So it is good with clustering, and this particular algorithm is something which I have to write from scratch, right? So because to make it very much computationally effective and alter behavior to the way we want. And one of the alteration which I made to this particular algorithm is that usually when we do cluster centroid calculation, we take an average of it. But for this particular scenario, we are not taking it. And reason I will just explain in a minute. What we are doing is that we are taking Y max and Y min by 2, as well as X max and X min by 2, right? So we are trying to find the mid range of it. Why we do it? Because if you can see, if it would have been an average, it would have been coming here. But if you see the centroid is coming actually perfectly to the table leg center, right? What we want. And why it worked is the reason is that if you see if a robot is here, right? If robot is here and if robot is trying to check the obstacle, it will only see one side of that particular table leg, right? And doing this method, it actually helps me to not set a predefined offset in the calculation itself, right? It is managing it with the help of the data it is receiving, right? And it will be much accurate if it is near, and it will be depending on it will attain its accuracy, right? So this becomes very effective method to pinpoint the table legs in general, right? So once we have filtered, we have table data with us, right? We have, you can say table legs, potential table legs, right? So because it's not a single which will be coming, in this case, we are seeing 4, but usually we have much more cluster, which is coming from here and there, which is other obstacles there might be, right? So what we are doing is we are going for a polygon detection, right? And in this, what we are doing is that we are taking, so if you see this particular image, we have, let's say, around 4, 5, 6, 7, 8 points, right? Which is here. And what we are doing is that we are trying to figure out if the table itself exists in these points or not, right? So for that, what we are doing is that we are trying to find a potential polygon shapes with the combination of centroid points. So what I mean by that is that we are trying to pick 3 points at a time or 4 points at a time and seeing if it's a valid shape or not, right? So if you see, it's a multi-step process, right? And what we are trying to figure out is that we are trying to find a triangle or we are trying to find a quadrilateral, right? So this is what we are trying to find in general. And for that, what we are doing is that we are doing extremity check, right? We are doing distance validation and we are doing angle validation. So what is extremity check? Extremity check means is that once I have selected 3 points, I'm making sure if there is no other point in between them, right? So if you see, the top one are the rejected one and below green ones are the accepted one, right? So this is the reason why we are doing extremity check. Then we are doing distance validation, right? So if you see, this one is rejected because the distance is too high to be a table, right? And why? How we know that? We have a particular threshold which I have set in code, right? Which we can change dynamically at the runtime also. Is that we can adjust this value to figure out whether this particular it's a valid distance a table side will be, right? Because we know the table will be of a fixed length, right? So that is why we can perform this distance check also. Similarly, I also performing an angle validation check just in last case if to make sure that whether it's a particular polygon is actually a quadrilateral or triangle representing a table, right? Once we have figured out whether that we have actually concluded that we have a table with us, right? We calculate midpoints of that particular table. We calculate the center point of that particular table. And then we also calculate an external imaginary point outside of a table just to form a particular path from that table's robot current position to table position, right? And we determine this path with the help of nav2 path planner. So what I do is that after calculating this path, I send this path to not exactly. So what I do is that once I have this particular point, I ask the nav2 planner to confirm whether this point is reachable or not. So after that, we finally decide, okay, if it's a reachable point, then nav2 will give me a confirmation and the docking will actually happen. Otherwise, the docking will not happen. It will give me abort message, right? That docking is not possible because table point which we have selected is actually not a valid point, right? It is somewhere on the obstacle or somewhere in the zone where it should not be. So this is how we are actually doing it for the table detection, right? So this was the complete detection part of it, right? Now let's come to the control part of it. When I was saying like a high level control. So what I mean by high level control. So nav2 itself is a very high level in itself, right? It's not a very primitive. It's a very good nav2 stack is very, very high level in nodes we have, right? We have path planner. We have a very complicated system, right? But we also need something because our operation does not look like that, right? I cannot go to every time to say, okay, I have to go to this point or it's not feasible enough, right? So for that, what I have done is that I have rewritten some other layer of on top of nav2, which is helping us to do high level operations. High level operations means that we are able to patrol the environment, right, continuously without until we request for a state change. We are able to dock it once we have found the table. We are able to move from point A to point B. Once we have figured out, okay, docking has happened, we can also undock it and we can also move to idle position if something fails up, right? And this is done using the concept which I have, you can say, innovated is known as state machines, right? Although it exists in ROS1 version of it, right? For ROS2, I have to rewrite the library to accommodate the things in my way, right? So, and it is working on the concept known as automata, right? So it behaviors, this particular state machine governs the action and behavior, right? It is a high level of operation manager, right? Which is written on top of nav2 and all other system, which is running behind it, which includes the other nodes, which I have mentioned earlier, right? We have elevator management, right? This is a single node which manages the footprint as well as the elevator at the same time, right? And it changes whenever a request is received. And then there is a docking action server, right, which is responsible for performing the dock, right? So this is how the state machine looks like, right? We will be seeing this in practical just after we deep dive into the demo part of it, right? So, and how the data flow looks like, right? How the request is coming. So this is the complete graph which I just talked about, right? It will be very much, you can say, techies will be able to relate much more with this, right? I personally do much more with this, right? So if you see this scan, right? Scan data is coming to filter node, right? Finally, with the help of map data and scan data, we are moving to clustering node, and clustering data is going to detection node, and detection node is finally giving you table position. Similarly, we have robot command, which is a high-level command like patrol, move, or dock, undock, these kind of commands, which is controlled by a robot control node, and it controls everything depending on whether it has the complete information with it or not. It also checks that performs the docking, and it also do the elevator control in general, right? So if you see, we are only having the one which is thicker in nature, right? The scan, the set elevator, and the command velocities are the only thing which we are actually sending or receiving from the real robot, right? Rest of the things connections which we see are the one which we have created to govern the system, right? And if you see, this one is action server, right, which we are using. These three are actually the services, right, which is also responsible for various other operation which will be performed in between, right? Finally, this is my web application to control and govern everything, right? The idea behind this particular application is that once we have it, right, once we have, you can say, this application upfront with us, we actually don't have to look and go for Arvis, right? So that is what I was planning to. There are definitely a lot of challenges in to do with such an application, right? One of being that we do not have a lot of native libraries does not work very well with the ROS2 system, right? So for overcoming this, what I have to do is that I have to rewrite a lot of JavaScript function as well as backend also, right? From the ROS side also to, or even I have to hijack a couple of libraries to make sure that it works with in the intended way. And what we are able to do, if you see from the screen, is that this is a parameter server, right? It controls the parameter of the road at the runtime. So for example, we want to change the distance of tables, right? Or we want to reduce the size of table. Let's say for a new table has been, we want to do with a new table, we can do, right? We have an angle tolerance also. We also can change the clustering points, right? Which clustering algorithm. So these are a couple of critical points which I have mentioned here, right? There are a lot more parameters which is also running on the backend, but since there is a limited space on the screen, I have just keep the most critical one on the front screen. We can get parameter, we can set parameter, both of them are possible, right? The center one which you see is the trash table detection part, right? So what it does is that it gives you a brief idea that if table is being detected, then how much of table is being detected. So you see the purple part is the actual legs of the table, and the yellow one are the midpoints of the table. And we are able to see if that threshold which we have set, then how much that like is really inside that particular threshold. So we can adjust, by seeing this, we can adjust the min max value also, so that it gives us better control over the table detection part. Finally, we have robot localization part, right? And if you see, there is a very small red arrow which you can see, and that one is responsible for showing you the robot position and orientation in real time, right? So as robot move, we will be able to see. And this is completely new. This is a canvas function which I have written to showcase it on the screen, right? Helps you a lot to visualize the robot location and what robot is doing, right? So it's a very great, you can say, addition to the website. Finally, we have a petrol, right? So what you see here is in commands, which I was talking about, the high level commands. And we can select the command and we can send. You will be able to see that log messages, which is coming from the state machines, right? And we will be able to see that how that particular system is working and which state it in case if something has failed. Because to be fair in robotics, right, there always need a little bit sprinkling of luck, which needs to be there, right? Although we try to strive to make the system as best as possible, right? But still, a lot of edge cases do occur, and we always have to figure out, right, what happens. So this is the reason why I have also given this particular option, that where we can see that what robot is thinking actually. Finally, we also have this one, right? This helps me to tell if docking is happening, then at what stage the docking is. In case it fails, it also represents some different colors, right? And it helps me to send the command directly also. So these are a couple of, you can say, website edition which I did, right? Apart from the joystick and all other, which you can see on the screen, right? So yeah, so I think we are on time, right? Alberto, I think the lab is about to start, right? So we can go into the real lab,
Yeah.
right? And try to test the system, right? It will be just a couple of minutes, right, before the lab will start, right? So uh, so the thing is, if you can see on the left side, we have a dock which is being performed, right? And if you see the table is quite close to the wall, right? And robot is able to detect and go. Similarly, in the second one, you see that what we are trying to do is that we are taking the stress table, we are picking it up, and then finally we are moving the stress table to the second room, right? And it will help, right, to like what we will do is that we will definitely test it limitations, which we will, right? And for the starter, we will pick up a very base case, right, where we want to perform the activity from picking it up to the end, and then we will test out with different scenarios. Right? So with this, I think let me just share my screen, right, in a couple of minutes.
Yeah, so actually we moved your reservation to be a bit earlier even, so
Yeah.
but yeah, so
Yeah, just in
I'm
a couple of
I'm
minutes.
eager
We
to
can
see the tests in the real robot.
definitely.
And by the way, really impressive presentation. Very detailed. Very yeah.
Thank
It
you.
was really nice.
So just system is coming up, right? In just a couple of minutes, we will be ready to deep dive into the demo part of it, right? And I'm very happy that we will be seeing the hard work of quite some months into action, right? So
Yeah, it really looked like a lot of work from everything you were showing and explaining.
we can perform doc, Alberto, but can we request Rodrigo to keep this table somewhere in bit?
Yeah,
Yeah,
yes.
yeah,
So
because yeah.
what?
We can perform, but I want to start with a very base case, right? To showcase the completeness of the project, right? Then we can test it out with other possibilities.
Yeah. So where would you like the table to be?
Anyway, it's very close to the very in a very corner, right? So
Ah, okay. Okay,
yeah,
so
I'm just sharing my screen also in just a minute.
yeah, I
It
don't
will
know
help us to see
if
also.
Rodrigo or somebody here or Ricardo is listening. Let's see if they can go there and
Okay, so I think it is visible to all of us, right?
okay. Okay, yeah, I can see the cameras now. Yeah, so I guess it's to move it a bit away of the table, right?
Yeah.
Mm-hmm.
Although I will just for the starter, it will be able to detect it, but I don't want to dock it from there, right?
Okay, let me try to do it myself. If not, just one second. Okay.
So as we can see, right, it knows where the table is, right? If you see it very closely, right? So if you see, we are also seeing some numbers, right, which represents if I perform the docking, which one of side it will pick, right? And the one red dot is the center of that particular table, right? As you can see, it's not completely detecting because what is happening is that these two legs are very parallel to each other, right? Robot is not able to find that particular reading, right? So once I move it, it will start. If it is able to detect fourth leg, it will update the shape also, right? So what I will do is that I will connect it first. So as soon as I connect, you can see that it will start coming, messages will start coming here, right? We can see that map is also updated, right? So after that, if I see the get parameters, you can see the dimension of the tables has been updated, right? We can see a lot of other parameters which is there. So if you see this, I can also shrink the parameter, and once I update it, right, it will update in the system also, right? Last thing is that which we can do is that we can find table to make sure the table is detected. I'm doing it first time. I'm doing it manually. Later on, we will be trying to do it completely automatic also, right? It's a complete autonomous system. We don't have to intervene at all, right? So, but for this particular demo, I'm just like for a starter, I'm just doing it manually, right? Then I'm hijacking the system. I'm asking it to directly go for a dock, right? Usually the state machine works in a fashion where you want to actually do like a petrol, right? We don't want a specific location it to be, right? We want a petrol, right? I will try to dock it, right? Let's see how it works, right? Because system always works in a very mysterious way. You can see that it has updated, right? It knows the path. It also have updated the path. You can also see that it has figured out the fourth point, right? Now, if you see that it is actually going to the external point, once it has reached to the external point, it will rotate towards this table. Then it will go inside that table, right? And once the table is detected, right, I will keep stop also ready in case something happens, right? So if you see now it is reaching to the center. It has reached to the center, right? Once it has reached to the center, it will align itself to make it easier to come out of table, right? As you can see, it has already picked up, right? And it is wobbling because the weight distribution of the robot, right, is a little bit uneven. So it is wobbling. But once it moves to the forward, it will go very smoothly, right? And you can see, right, it is taking table to the second row, right? I see it has picked up a little bit off, right? Might have happened during the reverse of it, right? So it is taking, the final goal is this, right? This particular point. If you see there, these are a lot of waypoints which has been marked, right? I think it has moved out of table, right? I think docking because the lifting has not happened properly. So that might be the reason, right? But once it has came back, it will go navigate back to the original point, right? Which is the external point, right? Which is marked in this particular X, which you see on the screen, right? And it will, if you see the state machine is already updating a lot of things, right? And if you see that it will go to halt and then finally move to ready. So you see the state machine has moved to halt and then finally moved to idle state, which is means that it is now ready for the next operation if we want to do it, right? So this is how in general the system works, right? Obviously, there are a lot of if and buts which happens during these operations, right? And if we want, we can keep the table again back to some other place, right? And we can test out the system also. Right. So
so let's see if Rodrigo can put back the table somewhere else now.
Yeah, let me move the robot from a better position, right? Yeah. So we can put the robot back, like the table back, right? We can test out for other possibilities also, right?
Yes, I saw in the cameras that Rodrigo was around, so let's see if he can.
Yeah, let's wait. Meanwhile, let me show you one more thing. So you see that I have changed the state to petrol, right? And once I execute it, you will see there are a lot of other points which came into the picture, right? So what it represents is that now robot is actually in a petrol state, which means that it will keep on navigating the system, right? Until it finds a table. So this is what this particular behavior looks like, right? It is constantly checking for new tables, right? It is also, meanwhile, it is also doing the patrol, which is around the, you can say, complete environment, right? So, and if I want, I can do the stop also, right? Which changes the state back to, and it will clear out all the waypoints which is in the environment, right? So let me halt it. You see that waypoints has been cleared, right? We are no longer able to see anything, which means that robot is again back to the standard part, right? And it is again ready to take other operation. So for example, now we have a table, like let's go somewhere here, right? I'm navigating it back. So we can do the docking.
Okay. So, yeah, Rodrigo just told me that the robot is low on battery, so let's hope that
Okay. Yeah.
that it doesn't turn off.
Yeah, I'm not seeing the laser. It's already like how much I think, because I'm not seeing the LiDAR data also. Let me go really close to this. Yeah. So if you can see that it has updated, right? It knows the table has been like shown, but I'm seeing that it is inconsistent. So it is like not giving me a 100% feedback. So not an issue. Let's see if I can perform the dock, right? Okay, so now you can see it has started to perform the dock, right? It is trying to go inside the table, right? It has already selected the one as the side which it will be docking through, right? And you can see it's even very close to the system. It is able to detect the table, right? Right. So it is not fluctuating enough and performing it quite good, right? And let's see if elevator works properly this time. So we will be able to. Yeah. Okay. So you can see it is moving, right? So it is taking the robot from its position to the end position, right? I also wanted to test out a very edge case, but let's see if time permit us this, right?
Yeah, more than time, I think that the problem is going to be the battery, but we can still try.
Yeah.
So what was this last case that you wanted to test?
So I wanted to show you, although it's I have a GIF also, right? Just to showcase also, right? So this is the perfect case which is working currently, right? Which is where you have a table. It was very close also, but we were able to figure out, right? Even if it is coming back, it knows the table is there,
yeah,
right? So this is working out. I wanted to show you a diagonal version, right? Where the robot is exactly diagonal to the table, right? And in that case also it will work, right? If you remember the first slide which I showed, there was a GIF, right? It was showing as a diagonal entry point, right? Which is happening. So, and also you see these bars are also reflecting all the states which is happening, right? So I was looking to showcase a lot of other things which is there, but I believe I'm short on time, right? So let's see. Any other case, Alberto, you wish to see in this, or
I think
we are good?
we can leave it here, yeah. And
Yeah,
yeah, I think
because I
again,
have endless things to
yeah.
show. Yeah,
No,
yeah,
no,
I will.
yeah.
Yes.
I mean, you have already shown 2 cases, and yeah. So let's yeah. So let me just give you an applause first of all for the presentation.
Very much. Thank you for that. Yeah. So
Let me switch here to the.
yeah, let me unshare my screen on this.
Where are you?
I think my system has.
There we go. Okay, there we have you. All right.
Yeah.
So again, let me remind to the audience, it's time for the questions. So write down your questions there in the chat. Then yeah, let me start myself. I have some of them
Sure.
written down here. So many things, because you talked and you explained and you showed many different things. So
Yes.
for instance, all this part that you created using state machines and so on.
Yeah.
Did you consider using behavior trees?
Yes,
at
I
some
did.
point?
Yes, I did. So initially, I was planning to do with behavior tree only, but the thing is, there is two challenges which was there. First of all, the detection itself was a very complex in behavior, right? So the lack of time is definitely one of them. Second thing is that exposure to the behavior tree, right, which was required from my end to do it, right? So I was thinking to do it from that way, but what actually the why I decided to do with this particular thing, right? Why I decided not to do with behavior tree is that I wanted to try for myself to implement as a state machine, right? Because what happens that it needs, right, there is although a lot of use cases does work well on the behavior tree, but sometimes we do wish that we have a simpler mechanism to do it, right, not going into that much complexities of implementation, right? So that is the one of the reason for my choices, right? To pick up, not to go with behavior tree and go with the completely new framework, which and a way to do it, right? Because I have faced this kind of a challenges before also, right? Where you want to do in Node, you want to do things in a straight point of view. For example, in a sequence, right? If I'm from point A, B, C, D, you only want to perform 4 tasks, right? And it always comes back because if even the easiest way to do is the timer and then cancel the timer. It's a very, you can say, not that pretty solution to implement this, right? So I decided to implement a new way to do it, and with the help of state machine, that is what I have achieved actually.
Okay, cool. So
Yeah,
I can see many questions here already. So also, I was interested on that part that you showed in the website where you you had that panel, let's call it like that, where you could get and set parameters.
yes,
And I understood that you can change them live, right?
yes, yes.
And so in order to do that, are you using some kind of a special node like lifecycle nodes, or are you using regular nodes, or?
So again, I will answer this question in 2 steps, right? First of all, the initial idea was to implement it as a lifecycle node, right? But it does not change the fact that even then you need a dynamic parameter configurations, right? To set and update parameters on the runtime. So what I did is that although I was thinking to implement lifecycle node, but lack of time is again something which stopped me to do it, right? I was thinking that to reduce the complex computational, you can say, load on the robot itself, what I can do is that I can only bring the system when it is needed with the help of lifecycle mode. And the control node was also capable of changing the state of other loads as and when required. For example, elevator is only needed when you are actually elevating or like you are elevating up or elevating down. In rest of the scenarios, you actually don't need it. So that was the reason why I was considering lifecycle, but I was not able to implement it in time, right? It was a lot of other things which was there which needs to be implemented. So I have not considered in moving in that direction, you can say in favor of time. But for parameter server, right, what I'm exactly using is dynamic reconfiguration, right, which is implemented in every node. And whatever critical parameter I'm doing is actually publicized as a parameter outside of node. So you can change it from launch file, you can change it on real time, right? All of that works, right? For every single node which is there in the complete project. And all the critical parameters are not hard-coded, right? It's completely dynamic in nature. Yeah.
Yeah, really.
Gives you a lot of flexibility actually. So that was my reasoning for it.
Yeah, really, really cool.
Yeah.
This is something that, especially at the beginning of ROS 2, was something hard to achieve, especially without lifecycle nodes and so on. But yeah, so really nice.
I'm very impressed with lifecycle nodes, but I was very much tempted also to implement it.
Yeah,
but but I have to stop somewhere.
Yeah, and okay, let me start with some of the questions that I can see here in the chat. So, for instance, we have Miguel. He's asking, can you elaborate on how the path to the table is generated? How is one side of the 4 possible entries for the table selected?
Definitely. So I will just move to a very respective slide which I have for this particular question, right? Which is the external point calculation. All right. So it's a mathematical operation which I perform, right? So once we have figured out, I have a 4-point with me, right? Which is a potential table, right? We already know, or a 3-point of it, right? If it, in case I am only detecting 3 lakhs out of 4, right? After that, what I do is that I calculate midpoint of that side, right? All the side, and before that also I have to sort
Abhishek, 1 second,
Sorry.
because I think that we cannot see your screen. Give me 1 second.
Is it?
Where is? Okay. So you are screen sharing right now?
Yes, I'm.
Okay.
Let me reshare it again in case there might be some technical glitch. Is it visible?
Not really. It's
Weird.
I mean, I can see it, but it's like not well centered. Let me see if I can. Okay.
Let me reshare it again in case.
Okay, now we can see it. Yeah. You are in the external point slide, right?
Yes.
Yeah, okay.
Yes.
Now yes.
So you can see this particular slide, right? This is the image which I have generated specific to how I'm calculating the external point, right? So what I'm doing is that I'm sorting those points for first, right? And then finally finding the midpoints based on midpoint formula, right? Once that is done, what I do is that I finally calculate a line which is coming from center of that particular point to the midpoint, right? And on that particular line, I finally calculate a point which is outside of the table, right? In layman term, right? And once I have calculated that particular point, I send this particular point as the target point to nav path planner, right? I ask him to validate whether particular external point which I have calculated mathematically is actually a feasible point or not, right? So if it's a feasible point, then only I will try to talk it, right? I will try to formulate a complete path. So what I do is that once an F2 has confirmed whether that particular point is reachable point based on navigation stack, then I finally calculate my own complete path from robot current position to this particular external point and to midpoint and finally the center point. So all 4 points which is there are used for the calculation of particular robot, right? So this is how actually I'm doing this, right? So hope this answers the technicalities behind the calculation.
Yeah. So also I can see here another question by Miguel also, and it also relates to a question that I have. So I'm going to kind of
Please.
iterate both questions. So he's asking, do you have this state machine system accessible in some Git that we can use? Is it easy to integrate with other robot systems?
So what I have done for this particular project, it's inside my code only, right? But I'm definitely thinking to make it as a, you can say, independent system also, right? Which is possible, right? So which can be leveraged by other developers also to implement their kind of use cases for this particular kind of systems, right? It's a very pain in most of the people definitely have felt it, right? And so what I'm doing is that for now, this is only inside my code, right? Because that is how I designed it for now, right? But in future, I will definitely make it as a completely external package also, which we can import.
Yeah,
right? A class one approach.
Yeah, that'd be really cool for sure. And also, you mentioned that you had to almost rewrite also it was the clustering algorithm, right? So
yes,
and
I have actually tested out 6 of them to finally conclude on one, out of which two of which I implemented and using the most accurate one currently in the system, right, which was producing the result in that app, right?
Okay.
So,
Yeah. So let me go with one last question. Let me see. Yeah, for instance, let's go with Rodrigo's question. He says, I noticed that the alignment of the robot to the center of the table was a bit off. In both cases, it moved a couple of extra centimeters forward. Is that an easy fix?
yeah, definitely. Right. So what I think is that, see, what is happening is there was some implementation which I have modified in the end, right? And what it is doing is that it is actually updating the position which it has already known to the new position of the table, right? And so what happens that as the robot moves from its position towards the table, it updates those points 3 times in a row, right? After each successive completion of the point. For example, from external current position to external point, it will update. After that, it will reach midpoint, it will update. And what I understand it, because from screen, I was not able to assess whether it is going 100% accurately to the point or not. There was some other mechanism which I have not implemented. I was thinking to implement was to make sure that whether once the update request has come, it calculates the distance to manage the drift, right? How much it has drifted from its original assumption where the table is, right? So it is a very solid mathematical solution for this particular problem, but lack of time is something which I was not able to implement it, right? But it is one of the way you can fix it. And so it will make sure the center of mass of particular table is well aligned, right? But one thing which I also want to add particular for this particular case is that this is also happening due to the reason that the acceleration and deceleration of the NEF2 is not, you can say, consistent, right? It picks speed very fast and then so jerk is coming up. So that is also the reason why it is happening, right?
All right, Abhishek.
Oh.
So we cannot see you now.
Oh, so I think let me change my camera. I think my main system.
Just so that we can see you one last time here. Yeah.
Yes. Yeah.
Let me see. Okay, there we have you. And okay, I have a bit of a.
One more question, which I think Girish has asked. Yes, Girish, we can definitely do it, resize it on the runtime to any table which we want.
Yeah, go. Yeah.
And second question is also valid, Girish. We can, because I was thinking to show it that we can definitely bring the table back. I have tested out multiple times to do it, right? We can bring the table back to the room, right? So it is also possible.
All right, awesome, Abhishek. Then many thanks again. Congratulations for the presentation one more time.
Thank you. Thank you.
We can definitely tell that there's been a lot of work behind that. So yeah, we are going to be talking in the next days for the next steps, and congratulations on getting to the end of this masterclass.
Thank you so much, Alberto. And I really want to thanks everyone which has supported me in this particular journey. Right, me coming from a very non-technical, not exactly a non-technical, but non-robotics background to finally able to complete masterclass is a very much you can say a big journey for me at least. Right, and I want to appreciate everyone which has helped. Right, the mentors as well as the construct and my family and friends which has supported me throughout this particular journey. Thank you everyone for being there.
For sure. Congratulations and well done. All right.
Thank you.
So let's continue then with the ceremony. And the next presentation that we have scheduled is going to, we are going to switch to a different robot. Now we are going to move to a warehouse environment. And the next student that we have is Brayan Laura Ordoñez. And the title of his presentation is the following. There we go. Is enhanced warehouse robotics, localization and shelf detection techniques. So let me put here. There we go. There we have in full screen Alison. So hello, Alison. It's all yours. You can start already with your project whenever you want.
Okay. Hi, Alberto. Can you hear me and share screen clearly?
Yes, we can see it.
Okay. I start now. Okay. One moment, please. Okay. Amazon Kiva's robots increases sales from $30 billion to $300 billion, with 750,000 robots, 175% of product, changing logistics. My title for my project is Enhances House Robotics, Location and Detection Techniques. My project involves detecting the shelf picking it up, transporting it to a target point, and then setting it down. My project focuses on the following topics: localization, self-detection, approaching the shelf, navigation, behavior architecture, web page diagram. Localization. Localization is based on MCL. In the first video, you can see that localization works correctly. But in the second video, however, the localization fails. No? In this case, the robot is lost. In this condition, is unrecoverable because the point cloud has already converged. The parameters for the test were set to maximum of 2,000 particles and a minimum of 400 particles. The problem lies in the following: geometric similarities in your environment, symmetries in your environment, no? as seen in the map. The first solution is based on increasing the number of particles. This video was tested with the following parameters: maximum particles 5,000 and minimum particles 800. Thus, these advantages are here: high cost, computational cost, it can still fail, localization cannot fail, and everything depends on accurate localization. My solution is based in initial pose. No? The following steps were taken. Find a fixed point in the environment that can be easily located. This fixed point is the charging station. whose position is now relative to the map. Located charging station relative to the robot. No? This is achieved with precision because the charging station has reflective types. This is achieved with precision. Yeah, okay. By subtraction vectors, vector 3 is found. Apply a transformation to the map, this vector relative to the map. Finally, this position is published to the initial post topic. And at the end of the presentation, the results will be shown. Shelf detection. The detection of the shelf positions and orientation is simple when the laser can detect the legs through the reflected types, which is done through intensity. This graph shows the intensities captured by the laser when it enters the range. A threshold is defined here, and an algorithm is used to detect the center of the legs. The problem follower was as follows. The blue vector is obtained by request the transformation by robot laser link to a DOM. Point M is obtained by a vector addition of leg 1 to leg 2 and some mathematical operations. In this way, we can publish the frame of the shelf. This frame is absolute in always point to the center of the shelf, independent of the robot locations or orientations. Problem: shelf detection of range. This happens with when the robot is behind or of range of the shelf, and the laser cannot capture the intensities from the reflect types. The first solution is navigation through the map by setting multiple points until the shelf is found. This is a good solution because it allows the robot to cover of areas, but the problem is that it can take time to navigation through all the points. My solution is to detect the shelf legs through the laser readings, specifically the range readings. For this, the following steps were followed. Apply a filter to the laser readings, create a map of the laser readings, create a map, filter the laser map with the static map, shares of the legs in the filter map, and shares for navigation points. First laser filter. As seen in the first video, the laser readings contain a lot of noise. This happens when the laser readings hit the edge of objects or when these are shiny objects. The white square encloses the shelf. With this data, it's very difficult to find shelf legs. In the second video, the same data is shown after applying a shadow filter. With this data, the shelf legs can now be detected. Okay, create a map of the laser readings. To create a map from the laser data, we first need to transform each laser readings to the map's coordinate system. The result of the map created from the laser readings can be seen in the following video. The color scheme of the map is in the cost map to distinguish it better. Filter the laser map with the static map. Now we inflate the laser map and remove everything that matches the static map. This way, we are left with the dynamic objects that appear on the map. In the following video, the result can be seen. Laser map filter. We can capture object dynamics. As observed, there are still around arrows points on the map. Unfiltered points. These points appear because everything is based on the robot's position relative to the map, which is obtained from MCL and is not exacted. This is necessary to create to the map from the laser. This can be visualized when the robot rotates, showing how the laser readings shift from the map. This is shown in the following video. Here, and here, and here. Shares for the legs in the filter map. Once the filter map is obtained, we can share for the legs, shelf legs. We do this by examining by size of the blocks and distance between them. Sometimes we will only detect 2 or 3 or 4 in the base case. Then we proceed to find the centroid of the set of points. Since this is not precise, we rotate the robot while determining the position of the shelf, the purple point. In the end, we take an average of the closest points. We now have the position of the shelf, but there are still some problems to solve. The goal is to approach the shelf in such a way that the reflective types are detected for a precise approximation. We still need to determine to the direction of the shelf. The direction is difficult to determine due to the noise accumulated from filtering and transformation and the fact that the 4 legs are not always detected. If I navigate directly towards the shelf, it is likely that the reflective types will not be detected. Share force navigation points. I need to find a navigation points that allows me to cycle around the shelf to always detect the reflect types. For this, the following steps are followed. I project the line connects the robot on the center shelf at a distance 80 centimeters. This will be my first navigation point to evaluate. From this point, I circle around the shelf with the same radius, tracing a cycle around it. The order navigation points will be alternate 1, 2, 3, 4, 5, 6, 7. These navigation points will be evaluated with a global close map to verify if they are reachable. The following videos show how the algorithm works in positions where the shelf is difficult to locate. The following steps are followed. I rotate the robot with storing the detected shelf center indicated by the purple centers. Here, errors here detected. I can be observed that there are purple points appearing in the outer parts of the map. This is due to the MCL problem explained earlier. The average of the closest points is calculated, the shelf is located, and the navigation point is determined using the previous algorithm. Navigation is cancelled when the reflect types are detected. At this moment, the direction of the shelf is captured and these coordinate frames are published. In the second video, you can see how the navigation point search is conducted. It is shown for better visualization. Please rotate the text in purple point. And says for navigation points with red arrow. Approach shelf. For the approach shelf to shelf, some control points are defined to enter precisely into the shelf. First target control point. The first frame shelf mid-legs frame has already been determined from this frame. The control frame is published at a distance of 35 centimeters. This is explained in the following graph. This will be the first control point to reach in terms of distance and direction. We need a distance of 25 centimeters, which is the radius of the robot, and the tolerance of 10 centimeters is defined for correct position and alignment. The expected result is shown in the figure on the right. A second target control point. Once the first point is reached, we cannot enter directly into the shelf as the main debit quickly, even if the robot has good orientation control. For this, we defined a second control point located at the center of the shelf, second control point. In this way, we ensure that the robot position itself with great precision at the center of the shelf. There are some considerations to take into account to achieve a good approach. First, all the published frames are referenced to the odometry. The control error, this is due to the following reasons. The control error will be obtained by requesting the TF of the robot with respect to each control point frame. For this reason, we need an inertial frame. Therefore, we cannot choose robot baseline. We cannot choose map because the published time is too slow. The frames we will use it for control will be those obtained last. There will come a point in the process where we will lose the laser readings due to its minimum range. From this point, we will use the last publishing frames. We have to use the last frames because the odometry accumulates error over time, and we need to minimize this error as much as possible. Navigation. For navigation, I used the rotation scene controller as a secondary plugin. As seen in the video, this allows us to first apply a rotation to align with the path and then follow it. First rotation, align in the path. This helps us follow a path when we are very closest to an obstacle, avoiding curved trajectories. Behavior tree architecture. I based this on the architecture behind the NAT2 system. For this, H algorithm explained previously was converted into a ROS service server. Clients were created for each of these servers, and these clients were paired in behavior tree nodes. These are my primary behavior trees. In this way, I can call all my servers in my behavior tree. Localization server. It allows me to send an initial position to MCL once the sharing station is located. Find object server. Find object is allow me to locate an object such as the sharing station or the shelf using the types. Find lake shelf server. It's allow me to locate the shelf based on the laser range readings. Find night point server. It's allow me to find valid navigation points. Approach shelf server. It's allow me to approach the server at various control points. A client for navigation to post action server was also created. This way, I can access navigation from my behavior tree. Additionally, some auxiliary behavior tree nodes were created, which are the following. Publish transform, responsible for publishing all transformation based on the detected positions of the shelf and the charging station. Shelf handler. It is a handler for the RB1 based platform. This publishes on the topics elevator up and down. Change footprint, responsibility for changes for footprint depending on whether the robot is carrying in the shelf or not. Delay node and action node responsible for generating a delay necessary for the stage time when lifting the platform and other tasks. And not got captured node, a behavior tree node responsible for subscribing to the node post to reset a navigation position. This will be used for the web application. Web page diagram. I will now briefly explain the implement web page. I have task buttons that perform specific tasks. These buttons publish via road bridge to the topic BT selector and a node subscriber selector node and executes the required behavior tree. I also have a launch servers button and stop server buttons. These buttons make a post request to a specific route, and my web server handles launching and stopping the ROS launch files. I will now explain implement behavior tree, localization BT. First, I have a sequence inside it. There are reactive callback with two nodes. One of them is the find object client, which takes the object to search for as an input and outputs the position of the station. The second node is a tour node, which is a synchronous node allowing for reactivity. This will allow the robot to stop turning once it finds the charging station. The output port of the find object client node will go to the localization server. The localization server will capture this position and publish an initial position. Please, Alberto, could you connect me to the real robot?
Are you in a project?
One moment. One moment, please. I connect.
Okay. So have you done a booking for the real robot?
No, don't.
Okay. Are you doing it now or?
Excuse me?
Are you doing the booking now?
No, one moment. Robot.
Okay.
One moment, please. Sorry.
Yes, don't worry.
I can reserve for mm, 12 p.m. 20,
Yeah, just do. Okay. Yeah, that is showing your local time, so I don't know which. Do this one. Yes.
okay.
Yeah.
Okay.
So now
Okay.
you should go to the project. Okay.
Starting in 4 minutes.
Okay. I can wait a second. Let me.
Okay.
I can. I can change it so that it starts earlier. It starts now. Start on. Okay. Can you refresh the project page?
Okay. One moment. Okay. I can connect.
We don't see the I don't see the project
Sí, sí.
page. Okay, now I can see. Okay, yeah. So now when this finishes, you should be able to connect. Okay.
One moment, please. I'll configure some things. Okay. 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 One moment, please.
We don't see what you are doing now.
Sí, one moment,
Sorry.
one moment.
Okay.
I install some things.
Okay. Well, you can show us. It might be interesting also to us.
Okay. I use it behavior 3.
Okay. You are
Package.
installing that.
Okay. And view for my web page.
Okay.
I need web page address. Or I need install things for post requests in my web.
Okay.
Okay. Okay. Okay. Okay. Okay, I run road bridge. Okay. I run.
Okay, so we can see your webpage now.
Okay. Okay. I will demonstrate everything discussed on the Red Robot. I only need to run the web server and Raspberries from the terminal.
Okay.
I need to set up Raspberry. I need to set up Raspberry and also the web page address for the post request. I connect. With the launch servers button, I can run the navigation and servers. Okay. As you can see, the map is now available. This first button calls the first explained behavior tree in its localization. Um, um, okay, okay. Our error is here. Okay. I will turn the robot so the localization can be observed better. Since this is very quiet, I will position it behind the charging station. One moment. Okay. Okay. I need localization button. Robot is turned. As you can see, the robot starts to turn until it detects the charging station. Once detect an initial position is sent and the robot is located. As you can see on the map web page, the robot has appeared. Okay. I will now execute the second behavior tree, find shelf. Okay. As you can see, the robot starts scanning for the legs of the shelf. It is purple point, the text. Red arrow is navigation point set. This initial navigation is cancelled once both legs with the reflect tapes are detected. Okay. Shelf is appeared in the map with direction. I will now approach and pick up the shelf. A new navigation point is launched towards the frame created from the detection of the reflected types. The process is carried out using the control points. As you can see, footprint is changed. One moment. Okay. Okay. Now I will proceed to move the shelf to a position behind. No. Excuse me. I select a drop-off point for the shelf. I select four options: A, B, C, D positions. I position and the carry and discharge shelf, and the position. Okay. I think I click in the position is robot is here. My file. Yeah. Okay. Okay. Now I will proceed to move the shelf to a position behind the robot. One moment. I will move the robot to a distance position. I will move away. Moment. Find shelf. I find shelf. Sharing navigation point possible. It's navigation cancelled when reflected types detected. Approach and pick shelf. Okay. Carry and discharge shelf.
Okay.
Okay, yeah. In the A position. Okay. Good. I will take the shelf to a complicated position in the middle. It is a complicated position. One moment.
Okay. Yeah, let's do this demo in the middle to see to verify that the robot is able to detect the shelf in different positions.
Yeah, yeah.
And then we will.
Could me help me, Alberto?
How?
Uh,
Do you want me to move the shelf manually?
yeah, yeah, yeah.
Yeah. Give me a second.
In the
Yeah.
center map, please. Okay, okay. Okay.
Is that good?
See, here it's easy since the tapes are detected quietly. Please turn shelf uh, uh, 19.
90 degrees?
See, please.
To where? To the cones?
Uh,
Or it doesn't
one-
matter? Okay.
okay, turn shelf
Okay.
because no, 19 degrees, please. Okay, in this position, I now have detection of the tapes. Okay, find the shelf, scanning map, sharding selects shelf, detects. Uh, okay, I find navigation point. Navigation point is cancelled. We detected reflect types and publishing frames. Approaching shelf. I navigate approach shelf with frames. This is the most difficult position to detect because I was behind the shelf, no? Okay. Now carry and check shelf in position D. Okay. Okay.
Something failed there in the delivery?
An error occurred because my main node BT node is file sometimes crashing. I don't know why sucks. Okay, voy a.
Can it be solved by restarting it or?
Yeah.
Okay, let's try it quickly. Yeah.
Stop servers. One moment. Okay, yeah. Okay. Okay. Launch servers. Okay. 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 In localization, I need change footprint. One moment. One moment, please. Without shelf. Okay. I execute change footprint. Um, we are. I going off the shelf. Moment.
Yeah, so now it's more complicated because the robot is inside the shelf, right?
Okay. See, yeah.
Yeah, I would say to that don't worry.
Okay, okay. Yeah, my
Yeah. So we have already seen quite some interesting demonstrations. So
lo voy a hacer manualmente. Oh, okay.
okay. So this is a live demo.
Okay, find shelf. Find point navigation is found.
Mhm.
Detect shelf is complicated. Is complicated. Completed. And approach and pick shelf. Enter the shelf. Changing footprint. Okay. Okay. Delivery shelf in point A. Delivery shelf sometimes fails because it waits for a navigation point.
Mhm.
Okay, it's work.
Okay.
Okay,
Okay. So I think we can leave it here, Brian, for the presentation.
yeah. Okay,
If you want to, yeah, show some
I have
conclusions.
some team's conclusion.
Mhm.
Using MCL and fixed reference points like the charging station significantly improves robot location and query. Detecting shelf legs using laser range with reflect tapes can significantly reduce shelf location time, enhancing system efficiency.
Mhm.
Behavior tree architecture enhances automation control nodes, reusability, scalability, and reactivity, simplifying text execution and increasing productivity while reducing errors. Uh, I have improvements. Applying life cycles to edge service could provide complete control over their management. Combining the shelf detection algorithm with navigation towards predefined points on the map while detecting the shelf legs will enhance system robustness. An improvement would be to create behavior nodes at the navigation system level, utilizing its existing control and action nodes. This would streamline the process and enhance system integration. Thanks, Alberto and Giris, for supporting in my project. I attentive to your questions. Can you hear me?
Hello, hello. Yeah,
Okay.
we were giving you a round of applause.
Okay,
So,
thanks for
yeah.
that.
Okay, yeah, so very, very interesting project, Brian. A lot of work behind also. I can tell from seeing everything. Then let's try to do a couple of questions at least, because we are a bit late on time. Then
Okay.
let's so one of the questions that I had here that kind of you already said something in your conclusions is
Okay.
so my question is after having worked with behavior trees for this project, would you recommend using them for if you are a ROS2 developer?
Well, yeah, I recommend because for the following reasons. Behavior tree architecture provides a not reusability and scalability project. The most important reason is the reactivity. No? Reactivity. Because here, one moment. One moment. This there is a reactivity. This is behavior is simple. There is a reactivity callback fallback with two nodes. No, one of them is the find object client, which takes the object to search for as an input and output the position of the station. The second node, the more important, is the turn node, which is an asynchronous node, allowing for activity. Okay. This will allow the robot to stop turning once it finds the charging station. This is the more important behavior. The output for of the find object client node will go to the localization server. The localization server will capture this position and publish an initial pose. Okay, aquí. Okay. This is behavior tree. It's a bit more complex, but it basically uses the leg detections algorithm with range readings while searching for the reflect tapes. The robot rotates within a reactivity fallback. In the reflect types are not found, a navigation point is searches for an execute. The navigation ends when the reflectors are detected and the orientation of the shelf is defined.
Yeah, so these that you are showing now basically are the behavior trees itself. So with all the different branches and behaviors and
Exactly.
what is going to happen.
Okay. Sí. Yeah.
Yeah. Okay, and Girish is asking here, in the web page there was a button which say execute all tasks. So if you don't need to do it now, but
I show. But,
if you click it in this button, all the behaviors will be executed.
Yeah. Execute, find shelf, and approach and pike shelf, and init localization. And show. I show. One moment. Okay. Fine. Execute all tasks. All tasks. Okay. About. Okay. Behavior 3 is the process as died. Okay. I restart servers. Okay. One moment. Stop servers.
So do you know, or have you discovered it, why sometimes the behavior trees die?
One moment. One moment. Okay. I found that the reasons. I find. One moment. The problem I found was a cache issue. Okay. Init localization. Robot. Execute all tasks. Okay. Robot is find shelf, detect, approach, and pick shelf. Okay. My behavior tree entire is that is okay. This is this. Okay.
Okay, Alison. Then I think we should leave it here already.
Okay. So, yeah.
Okay. So many thanks again for your presentation. Let me give you another applause.
Okay. Thank you for that.
Okay. So good job, Brayan. And yeah, we will be talking in the following days.
Okay. Thanks.
Okay.
Alberto. Thanks, Giris, for the supporting in my project.
All right.
Thanks.
Yeah.
Thanks for the course. In the process, I learned a lot about ROS2 and how to apply it to the red robots. Thank you so much. Okay.
You're welcome.
Stop
You're welcome.
I stop shares. Okay.
Yeah.
Okay. Thanks. I disconnect. Thanks.
Okay. Bye. All right. So let's continue with our last presentation, who should be already here. Yes, I can see him here ready. And the last presentation actually happens to be with the same robot, if I'm not wrong. So we are going to stay in the warehouse environment, and let's see the approach that our last student, Rubén Vidal, has given to this project. So let's see if we can hear Rubén. I think you are muted right now. So if you please can unmute and maybe turn on the camera as well so that we can see you.
Hi, could you hear me?
We can hear you, yes. We cannot see you so far. I think, wait, you are here. Give me 1 second. Let me see if we can. Okay, now we have you. Yeah, we see you and we hear you. So yeah, it's your turn. You can introduce your project and start explaining yourself.
Okay, thanks. Can you see my screen?
Yes, we can see it.
Okay. So I'm going to present my automated shelf repositioning in warehouse environments. Warehouse environments are being revolutionized by the rise of autonomous mobile robots, transforming this industry. These cutting-edge robots supercharge efficiency and productivity, seamlessly handle inventory management, picking, packing, and transportation. Equipped with advanced sensors, such LiDARs, AI algorithms, and real-time data processing, autonomous mobile robots can navigate through complex environments with precision and ensuring safe interaction. The topics for this project is the setting the NAP2 framework, looking for the shelf, and the approach behavior, and the laser noise. So first of all, I'm going to talk about setting NAP2. I create a map, and this is the original map, and I found these kind of problems. The first problem is that when I set a goal and generates the path which is closer to cones or corners, it fails sometime or multiple times. Another error is the laser noise with the new stickers. And third is the not to go fail multiple times due to a huge footprint when you have the shelf, when you lift the shelf, and it cannot handle goals that are behind it correctly. So how do I solve it? First, I edit the static map. I repaint and remove the curves and cones almost entirely to reduce those failures. It's a simple approach. Reduce the rolling window, which is a window where the obstacles through close to the robot are being actualized, and I change the global cost map and local cost map parameters dynamically. And finally, for the final problem, I use a rotation shift controller. Rotation shift controller, we check the roof heating difference with respect to the robot and the new path. If inside a threshold, it will pass the request onto a primary controller to execute the task. If it's outside of the threshold, this controller will rotate the robot in place towards that path heating. And this is an example of using rotation shim controller in the warehouse environment. Can you see the video?
Yes, we can see it.
Okay. So the second topic is looking for a shelf. Is how do I detect the shelf? Well, I performed this task using the laser list of intensities of the LiDAR scan, which has a 2007 degrees of range. And I calculate the index value against the other ones, because I found that the threshold is around 3,000. And then I do with the first differential algorithm to detect the change through the intensity list, and then use this to calculate the distance and the angles, and then use trigonometrics to find the shelf point, which is a point what I use to get close to the shelf. When I test this in the real robot, I see this problem. For example, I detect the shelf, but also I detect the docking station, which has similar values to intensity. So how do I solve it? Well, it's pretty simple. I just calculate the distance between the legs, and with some logs of the bug, I found that the range of the left shelf distance is around 0.55 and 0.62. And with this, I solved this problem. Then for the approach behavior, first of all, I use the NAP, because it's pretty simple. I just publish an approach point to get close and then align to the shelf. But NAP2 is not accurate enough and frequently fails to get under the shelf. So I will find another simple solution, which is a simple approach follower, looking the transforms between robot-based link and the approach point using a gain proportional. Very simple. And finally, when everyone leaves the shelf, and I found this error, which is a laser noise. This doesn't occur 2 months before or 1 month. I think it's to the for the new stickers of the shelf to detect whatever it is in front or back. And for this, I solve it by using a laser filter package of ROS2. I use a shadow filter. Usually, the shadow filter is used to eliminate shadows detected in later data, which is useful if the shelf is creating shadows that result in noise, like in this case, for example. This filter removes points considered as shadows based on the geometry of the data. Shadow filter works by analyzing the data to identify and remove points that are likely shadows. Thanks. Now I'm gonna present the Hi, Alberto.
Hello.
Yeah, can I connect to the everyone?
I think you should be able, or you don't have a.
I don't see.
Can you
Let
try
me-
refreshing? Yeah.
Yeah, exactly.
Okay. Yeah. Now I think it's there. Try closing it, Rubén,
Yeah.
and then you open it later. Yeah. Probably some kind of. Yeah. There we go. I don't know if you're explaining, but we are hearing like some low
Oh,
noises.
okay. No, I'm launched the not
Okay,
to
okay,
setup.
okay.
I launched the scan to filter change and the entire not to configure.
Mhm.
Then I just launched the web page setup, where I launched the HTTP server and the WebSocket to use a ROS bridge in order to communicate the topics of the real robot with the web page. Okay, so first, we want to localize the robot by itself. So I launched the localization server,
Mhm.
which performs a square test to see if it's running or not. It's running. there is a sense of fail. So, which I launch again. You can launch multiple times. Usually, it's when you launch 2 times, it's a success message, and the web page receive those messages and see the result.
It looked like it was good, but at the end,
Yeah. It's a kind of strange. I don't have the enough time to debug this behavior, but
so now it's correct.
yeah, success. You see the result is true. So now we want to launch the patrol server, which launch a set of waypoint following, which are 4, and in order to found the shell. Okay.
What should the robot be doing now?
I don't know. It's performing the task. Yes. Oh yeah. Oh yeah. I didn't mention, but when the NAP2 reach 1 goal, I everyone do a rotate to the left and right in order to still search the frame. For example, you can see the result is true. We found the shelf one, and the logs are the same. So when you found the shelf one, the NAP patrol behavior stops, and then you can activate the approach server. Here I used a low values of velocity, because usually when the robot, when the robot moves, you can see the shelf point moves too. So even if the laser, the frame publisher frequency is equal or very similar to the laser frequency. So that's what I use a slow movement. Now that I reach the approach point, do the do the alignment for the frame. It's under the shelf. I'm going to move to another position to activate the self-position server to reallocate to the correct position. Hello?
Yeah, hello?
I can see the camera.
The
wrong.
camera, okay. Try refreshing, Rubén, the camera windows very quickly. Or if not, close and open again the window. There, yeah, there they are.
Difficult place like this. Okay.
So this last server, what is it for? Can you explain again?
Oh yeah. The last server, which is self-position server, is pretty similar to patrol behavior. I use three or four set of waypoints in order to navigate to the desired position, which is the and then, for example, the most difficult part for this project is the approach, because even if I use a simple approach against the NAP2 goal, sometimes even if detect the align correctly with a minimum error, if you don't get under the shelf with the correct position, like we can see here, when the robot goes to backward, will collision, like in this case, for example. Like I said, that's a mistake. Now I'm gonna cancel this because I false the last position, but I'm not gonna send it through this position because the robot fails to approach.
Okay.
I can use the shell for the word.
Sound is a bit off now, Rubén.
What?
The sound is a bit off. I hear you very low.
Oh, okay. Can you hear me? No?
Now it's a bit better, yes.
Okay, okay. I'm gonna talk louder. I'm gonna use the button to elevate the shelf. Trying to perform the task again.
Mm-hmm. Okay.
Example in another place. Because we see that in this place, the first goal was to sit. So with the backward movement. Oh, I need to change the parameters because I restart the navigation. Okay. Those are the parameters for the shelf point server. Each shelf, the patrol behavior and shelf position server has his own client to change those parameters. So I use in manual because I restart the NAT. I put the robot in a run position. Oh. I need to start the servers too.
Okay, so now the behavior should be that the robot brings the shelf back to the initial position, right?
Yeah, exactly.
Not see that message.
I didn't see the.
Okay. Yeah, I think now, yeah, localization is missing, right? So
Is there a problem connection? Because can I restart the?
I would try stopping everything and relaunching everything from zero. Yeah. Okay. So we are connected back to the lab, right?
Yep.
Yeah, and Andres Alamo here in the chat was suggesting to name the different tabs. I think that's a good suggestion. Yeah. Yeah, especially when we are with so many tabs, it can get messy to know where what is running where.
This loading again.
Okay, what if you click there?
I can open the. It looks like a connection problems more than other things.
I think it should be fine. Yeah.
But
The robot is not moving, or
yeah, it's not moving. Yeah, it's definitely connection problem. So, mm,
hmm. Can you try moving it forward or backward?
yeah, I'll try
Nothing.
to. I can move it.
Okay, that's weird. With teleop, can you try moving it with the?
Sure.
Let's see.
Nothing.
No?
No.
Okay, I don't know. It's weird. Okay, well, never mind. I think we can also leave it here. So the only thing that we weren't able to see was the last server, right?
Yeah. Oh, the last server is just
To return it here, yeah.
turn here and then goes to everyone to the initial position. Quite simple, but due it to connection problems, I can show.
Yeah, so I think I think we can if it's okay with you, we can go already with some Q&A.
Sorry?
Yeah, if it's okay with you, we can jump to the Q&A session.
Yeah.
So let me write this here. Then yeah. So again, it's time now for the viewers to write the questions in the chat. Let me start myself. So yeah, you were using this waypoint follower that you were mentioning. So this waypoint follower is the one that is provided by nav2 by the. Are you using that one? Or which waypoint follower you refer to?
Oh, I'm not sure if I understand the question, but I'm using the simple API commander.
Okay, yeah, that was the question, yeah.
And the basic navigator to which I can share. I I use multiple classes. For example, navigation cluster, which has all the positions that I do, and I use the basic navigator here. So this is the way to do the patrol behavior task and shell position service.
Yeah. So the simple commander API. Then, but for the final approach, you said that you are not using navigation, right?
Yeah, exactly.
Yeah. So yeah.
I'm using a simple approach, which is I'm using a follow frame, which I read thanks to another class, which is listener frame, frame listening plus, which listen the frame or whatever you want based on source and project frame, and then update the post. Meanwhile, I'm approach. So it's a simple waypoint follower, which it's more precise than the NAP2, just for this case.
Still, you also mentioned during the presentation that for this project it's very important that the robot ends up in the proper place when it's below the shelf, right? Because otherwise, when it elevates the top of the robot in order to pick the shelf and it moves, if it's not perfectly centered, let's say, then there are going to be problems, right?
Yeah, exactly.
Yeah, so this algorithm that this approach that you are using here, do you think it's accurate enough? And if not, how can be improved?
I think it's not accurate enough. Maybe I can use another approach. Maybe being more precise with the actualization of the frame publisher in order to don't have error when you take the shelf point and you move to the robot to increase the error. That's one of them, and the other one could be that's it. I think maybe I could use something like with NAP2 using and testing different path planning.
Okay, so let me go with some of the questions that we have here in the chat. So
Oh yeah, I can see the question of Girish.
the first one, yeah.
Yeah, what would happen when the shuttle goes to the charging station and you see two reflex scans? You're looking for lexical changes, and what will happen at the charge station? Oh yeah, that's a good question. This project can handle the your question because when the shelf is in front of um, the the charging station, usually the shelf phone has not been detected good, and maybe I could use a different algorithm for this precise case. One of the
Yeah, I think so. I think that the second question is similar to mine. Let's go with Rodrigo's question. So he says, "Why did you have to restart nav2 so many times? How can you avoid that?"
Like I said during my presentation, I think that the reason why I need to restart a nav so many times is because I have a connection problem. So I don't see those problems during my tests, and that's one of the reasons I go home because I test the shelf position in different approach, different points, and it works. So for the second, what improvement will you make in the logic to make the robot get under the shelf properly while starting the software? Like I mentioned,
Yeah, so we have also a question 3 from Girish. Can you perform all the tasks with one click, moving the shelf to some other place and getting back the shelf to the original position?
no, I didn't prepare this behavior. You can use the servers one by one.
Okay, and so let's say to try to close the presentation. So what things do you think can be improved? Let's say the most important ones in order to make your project better or more robust.
I think that it's to get a more robust solution for the approach, which is one of the most important tasks for this project. And another one, I could say that I can use behavior trees, but as I see in this project, it's too complex for the tasks, for those tasks. I think so. Except if we put the if we put the robot here with the shelf, and the robot gets under the shelf, how to move through this place, well, I could prepare a task for this using behavior trees, and that's definitely.
All right, Rubén. So yeah, I think we can leave it already here. Thanks again for your presentation.
Yeah, thanks.
Any last words that you want to say?
Oh yeah, I would like to thanks to Gary and Rodrigo and Ricardo who has supporting me during this whole path to becoming a Rose developer. Thanks.
All right, Rubén. Then thanks again, and yeah. So we are going to be in contact in the following days. All right, so yeah, we can then close it here. It's been a long ceremony today with 4 presentations. Pretty different between them, using different environments, different robots. Pretty interesting, all of them. So I hope that you have enjoyed them. And yeah, I hope to see you all in the next final project presentation ceremony, which should be in around a month. So yeah, hope to see you all there. And remember to keep pushing your ROS learning. Bye-bye.
Alberto.